All right, so thank you very much for coming. And let me present our recent work titled Opening Up Kernel-bypass TCP Stacks. And this is the work led by my former student, Shinichi. And please go to the next slide. So let me first introduce my research group that we are organizing some network and operating system lab called NOP Lab, which sounds doing nothing, but we are doing a bunch of stuff on the other hand. So I think some of you had the many talks in course notes, and thank you very much for great feedback. And the two big project umbrellas we have is one, the secure networking in cloud and beyond, or we are trying to replace TLS over TCP in the cloud, and one big work just accepted to the IEEE security and privacy, and we're also doing some progress on making TLS handshake fast, including supporting the resilience on the post-quantum cryptography. And we also just having upcoming hotness paper, which about operating system or network stack level protection against website fingerprinting. So I'm leading a little bit security people. And we're also working on some traditional topic, including this one. And we're also doing some work on TCP connection migration, which is paper under submission, and so on. So we are a group of, say, several people and have generously funded some organizations. Please go to the next slide. All right, so let's start with the motivation of the work. So general understanding of the people or consensus is, so if we bypass the operating system to implement TCP, it offers high performance because compared to the patch-based development of a Linux kernel network stack, so we can have a clean slate design, removing unnecessary background compatibility or generality. And we can also benefit from fast packet I/O like DPDK to implement TCP, so this could be great. And we can also do different common case optimization from Linux kernel, like specific optimization for small request and response traffic, or widely called remote procedure call or RPCs. So those are all great things, but what actually looks like if we want to use such a kernel bypass stacks in practice? Please go to the next slide. So let me explain a little bit of background. So the TCP is still dominant even in the cloud. The reason is everybody loves TCP. So almost all the applications support TCP, almost all the remote endpoint, they also support TCP, and the middle boxes in the internet or even in the cloud, they're all designed to cope with TCP. Right. Next slide. So the ubiquitous deployment of TCP is not only in the internet, but it is also true also in the data center or cloud. If we look at the cloud, we have some lot of proxies, network observability software like Cilium, also like the Amazon Elastic Load Balancer. So many middle boxes even in the cloud, and they all interact with TCP. So we can't unfortunately live away from TCP. Please go to the next slide. So, but then, especially in the context of cloud, and a lot of criticism about TCP implemented in the host operating system arise. So one of the reason is the bad performance to send and receive small messages, which are very common in RPCs in data centers. Another common problem is like ability to handle large number of concurrent TCP connections, which is the often cited 10CK connection, 10K or connection 10 million problem in the context of internet servers sometimes. Also, like modern the hardware or servers, they have a lot of CPU cores, but unfortunately, traditionally Linux kernel TCP has not been very good at handling multiple CPU cores efficiently because of locking or some cache line contention or those kind of issues. So that is why many people, both in academia and industry, started building some clean slate, sometimes not, but anyway, so some kernel bypass TCP IP stacks on top of fast packet I/O, like the DPDK or NetMap. So MTCP presented in the 2014, and FStack from Tencent, IX from the OSTI, and to name a few. And there are many, say, the kernel bypass TCP/IP stack presented in major conferences almost every year. But the building practical TCP stack is a lot of work because, first of all, the TCP has a lot of extensions, and some of them are, which means that implementing, say, very basic RFC or like TCP timestamp or just RFC 798, it doesn't mean it's being the modern free-fledged TCP anymore, because a bunch of the newer extensions, including a fast open, multi-path TCP, etc., also, even without ITF RFCs, there are a bunch of, say, extension to TCP, for example, like the TCP small q or the TCP TSO sizing, or a bunch of extensions are in the production TCP stacks. So also, and the kernel TCP/IP stack has also long been evolved according to the report in the ASPROS 21 paper, and still now, even just within the TCP/IP stack, still 5 to 20% of the code has been modified every year. So it's still under the lot of development. So what those observations implies is that creating a practical network stack needs huge community support with long term, and at least for most of us, unless we are hyperscalers. So if we're just individual or the non-hyperscaler industry, if we want something fast, so what the stack we could adopt, pick, or build? Answering this question is one of the main goals of this paper. Next slide, please. But the main problem is that we really don't know how the proposed stacks in the literature perform in various workloads and compare to each other. This sounds quite simple question, but actually unanswered. When every time the new stack is proposed in the literature, then they make a very limited comparison, and in terms of with what stacks they compare and in what workload. So one quite possible reason is it's running someone else's TCP/IP stack is really difficult. It's very difficult, as we're going to show. So that could be the potential reason. So we are trying to answer this question. So there's the interesting observation from Alibaba presented in Usenix HTC 2023. They say hacking into those problems will take an unexpected amount of engineering effort with rather limited community support. Hence, building a new stack from scratch can be actually more time-saving. Of course, they are hyperscaler with a bunch of engineering resources, but definitely most of people can't afford it. So the major contributions of this paper is we addresses those problems. One is we compare 6 existing the kernel or kernel bypass stacks with exactly same application, hardware, and workload. Then all of those stacks are not from us. So I do some kernel bypass stack, but they don't include us. So it's provided free third-party experience of using or fixing existing stacks. So we found some bugs in existing stacks and we fixed it. So I think we believe we made a reasonable effort. So the short answer to the question about stack comparison is there is no single stack that always performs the best. So measurement methodology we took is quite simple. So the server side, we implement some minimum HTTP server, which just responds to the request from the in-memory content. But we test many stacks, and they all have different APIs or programming model, but we didn't take the approach like the implementing some sim layer between the stacks and the application. Rather than that, we implement the same simplest application logic optimized for individual stacks, because if we create some sim layer between the application and the stack, which may be advantageous to some stack, but disadvantageous for some other stack, right? So also stacks like demi-kernel is written in Rust, so we can't do that approach very easily. So for the client, we use just ordinary the work HTTP benchmark tool with Linux with slight modification to improve multi-core scalability. Next slide, please. So which stacks we picked for comparison is based on the architecture. We picked the stack as a base so that they present as different architecture as possible. So first comparison we took is MTCP, which runs collocate application thread and stack thread on the same CPU core so that they can communicate without taking a lock. So next one is fstack, and fstack on the other hand, it runs both the stack processing and application processing in the same thread. But it uses, for the TCP/IP part, it uses FreeBSD stack. And for IX, it's similar to fstack, but it uses LWIP and more, say, streamlined TCP/IP implementation on the stack, for the stack. And the task is very interesting architecture, and it runs stack on, say, one set of CPU cores, then it runs application on the other set of CPU core. So they are completely split, the CPU core and the thread, of course, between the stack and the application. And demi-kernel is, in terms of, say, stack application execution model, demi-kernel is very similar to IX, but it's written in Rust. So we pick those stacks for comparison. Please go to the next slide. So here are some details. So those stacks have different architecture, but what I want to highlight in this slide is some stack are, say, often used. So basically the point is that running someone else's stack is very, very difficult. So some stacks are mostly only used by the same authors. So some stack, a very limited number of stacks, or even if some stacks is used by someone else without original authors, they tend to be like the workload or some message size, for example, it can be quite limited. So this is observation we found. So we also found, okay, then it could be worthwhile we somehow run some make fair comparison between all of those stacks. Please go to the next slide. So here the performance of, say, the bulk data transfer performance. And actually in this experiment, interestingly, the Linux performs the best. So we definitely make fair comparison. So we disable all the TCP segmentation for all the kind of things because some stacks do not support it. So we are making, in terms of offload, we are making fair comparison. So some people ask me that why large send transfer matters in data center, but it actually does because we are moving to terabit Ethernet. So we have to fill the bandwidth as much as possible because a lot of data are transferred, and also we see a lot of data-driven workload, like even sending, for example, machine learning model over the network. It's a bulk data transfer actually, right? So bulk data transfer is very, very important even in data centers. So yeah, Linux performs the best. This is not very surprising. And yeah, so this is one observation. And please go to the next slide. And then we measure some idle time small message latency, which means that between the two hosts, just send single request, get single response, and no concurrent request or no other the application or something running to harm CPU. So this is like idle time. So just spending all the resources just to process single request and response. So demi-kernel does the best job for extremely small messages, like say 64 byte or 500 bytes. But as message size get larger, it is performing not particularly good. So again, so then the MTCP, sorry, can you go back? So it's interesting observation is like the MTCP, the performance very bad because it is really optimized for throughput, and in terms of latency, it includes the more context switches between thread compared to other stacks. I mean, compared to run to completion based stacks, so it exhibits the higher latency compared to others. Okay, go to next. So the next the experiment is connection scalability. So between client and servers, we issue say between 100 or 1600 concurrent persistent TCP connections and send and receive say very small messages. So this is throughput and higher is better. And this result is based on the single CPU core, except for tasks which needs at least 2 CPU cores. And so we see that first important point is so the demi-kernel performs very bad for this workload, and also the Linux also poorly performs in this workload. Okay. On the other hand, the IX does a very good job about this, say multiple times faster than other stacks, except for the MTCP. MTCP was bad for latency, but it is pretty good for scalability for the number of TCP connections. So can you go back to the previous slide? Sorry. Another important thing is like the F stack also performs very bad in terms of connection scalability. And as I noted before, an F stack uses FreeBSD TCP/IP implementation. So what this result implies is says some the kernel-based TCP/IP stack implementation has some problem about connection scalability. Please go to the next slide. So then another experiment we do is multi-core scalability. First of all, in this experiment, the IX had some bug so it wasn't able to show, say, 24 core the performance very well, and IX and also demi-kernel doesn't support multi-core. So we are only able to test 5 stacks. And in terms of multi-core scalability, and the task performed the best actually. So that is pretty interesting. And so IX did pretty well, but throughput increase kind of maybe stopped, maybe because of bug, but for some reason that throughput improvement stops to increase. IX probably even from 8 to 16, but TAS keeps improving throughput linearly to the number of CPU cores. So TAS seems pretty scalable to multiple CPU cores. Please go to next. So yeah, while doing this project, we faced a number of problems, and the first problem we faced is, or we had some question is, what's the best way to profile and analyze kernel-bypass TCP stacks? So in Linux, we have the path for any eBPF-based tools, so which require a tool which is pretty convenient to profile or debug the code or performance. But those tools require we have to know the code organization of the stack. That is okay for Linux because we know, I know Linux kernel TCP organization, and we can, if we don't know, we can just ask ChatGPT to explain that. But the kernel-bypass TCP stacks, definitely we don't know the code organization, so we don't have familiarity. So it's very difficult to debug kernel-bypass stacks. So there was an interesting proposal in NSTI 2022 called NSITE. It is exactly designed to profile the performance of network requests for the stacks which we don't know the code. So that sounds quite interesting and useful, but at the time of as of now, I don't think that this tool is available publicly, unfortunately. But I think the tool like NSITE has very good potential to debug kernel-bypass TCP stacks. Can you go to next? Then the question is for the future, should we enhance in-kernel TCP stack, or we should pick one kernel-bypass stack and should improve it? So the first concern about enhancing in-kernel TCP/IP stack is, as we saw, in the Linux and F stack, which uses FreeBSD TCP/IP, and it showed very low connection scalability or very poor performance when handling a lot of concurrent TCP connections. So that is very prohibiting. And since this may come from some fundamental problem like size of some TCP connection related data structure, so approach of improving kernel TCP stack may be quite difficult in this aspect. But on the other hand, the run-to completion model used by many kernel bypass stack, that could be the problematic in reality, because think about sending a lot of data, okay? Then we're gonna send a portion of that data, right? Then wait for the response or wait for the ACKs. Then we push the next packet based on ACK clocking. So which means that but when if we run both application and the stack on the same thread, maybe pushing the next data based on ACK clocking maybe a little bit delayed or getting efficient. So we have to carefully think about whether the model really fits for the real need, like the bulk data transfer. Go to the next slide, please. Yeah, so we don't have more discussion in the paper, so please take a look if you're interested. So here's the conclusion. So conclusion is like running someone else's stack very difficult, and no stacks actually serve all the workload, even simple one, very well. So Linux performs the best bulk transfer throughput, and demi-kernel achieves the best idle time latency without concurrency, and IX achieves the best RPC throughput, and thus shows best multi-core scalability. And we made some modification to the stacks. For example, like the task TCP stack initially showed even much worse performance in terms of bulk data transfer. We noticed that TAS doesn't implement the window scaling option, so we implemented that. So this kind of modification or bug fixes can be found in this GitHub. So just take a look and ping me if you have any question. So, yeah. Thank you very much. I think I see chat. Oh yeah, TCP client. So that's interesting. I didn't know the option John mentions. The accurate request is something taken from Quick, maybe. I remember that the Quick had some option about that.
Actually, the option I mentioned is not very important. It's a very corner case it originated in IoT systems where you only want to send one packet.
Okay.
But then Apple asked to actually change the rate for high rate transfers, but it probably doesn't impact. It probably doesn't impact this way.
Does it mean like is it the purpose is to let the receiver or some peer to sleep for a while before sending ACK or something?
Yeah, the problem, you don't want that happening with IoT. So you want to get rid of the ACK delay. And in really high rate, you only want one ACK for every 16 or even 32 packets instead of alternate, just to reduce the reverse path load. Anyway, there's just the two cases, but there's two options.
Okay. Sounds like we can do similar thing using user time option that the last was doing. Thank you very much. Any other questions?
Yes.
Sorry. Yeah, I wanted to present this in Cosmos, but I didn't make it. So.
So virtual is better that you reach people who couldn't make it to Cosmos as well. So
yeah.
So I was going to ask you, like, do you know why demi-kernel does so well for small packets? Is it because they have better ways of switching, less lock contention? What's the?
Yeah, probably they really pushed their strategy to optimize for that and didn't take much attention to other things. And also, it's a little bit unclear why it doesn't do very well for multi-connection cases. But it is clear that it performs really badly for bulk data transfer because their API, it forces the application split all the data into the empty side packet and put into the almost like a raw packet buffer, and so that makes things really bad.
Thanks, Michio. I was wondering,
Yeah.
so you did this cool setup to evaluate different stacks, realizing that this had not been done before. And I was wondering, like, could you use this to feedback how people are developing potential future stacks and to be able to cover cases that maybe they are not looking at because they simply didn't evaluate and compare them all?
I'm not doing such thing because I mean I do never intend to irritate others, and but simply like I mean I see actually informally see a lot of people actually struggle to make comparisons. So every time also I review the new kernel-bypass stack paper, and then yeah, of course the evaluation limited. I understand that, so I usually don't make the claim like, okay, you should compare with that, because I understand that. So. But yeah, but the thing, my point is that the people don't understand like that difficulty. So it's not only kernel-bypass stacks, right? Running someone else's some code is really difficult, simply difficult sometimes, right? So for me, like in my opinion, artifact evaluation thing is a joke, to be honest, because if we took someone else's artifact, of course, this is not all, a lot of good cases as well, but in many cases, like we have to use exactly the same setup, exactly the same script. And so artifact release doesn't mean actually the software release to be used by someone else, right? So it's specifically to plot the same graph or something. So making artifact available doesn't really mean, we can use that one as some comparison or something, right? I mean, it's not only network stack, but this particularly may be problematic for kind of low level stuff, I guess.
Mm-hmm. Cool. Any other questions?
All right, so maybe we are done.
Hey, thank you, Michio.
All right, thank you very much. Yeah.
Thank you very much.
All right, thank you.
Everybody have a nice weekend.
You too. Thank you very much. Ciao, ciao.
Bye.